Hello, everybody. Let's see you again, and let's start our lecture number 6. Okay, 1 second, please. And now we can start. So, this lecture starts with resuming the notions, the capacitance, and permittivity. Next, we will discuss basic configuration for capacitive sensor. You know, the capacitance value changes with variation in the geometry. We will focus in particular on nonlinear and angular displacement sensors and on force sensors too. Next, integrated silicon capacitive sensors are briefly reviewed, and some interface circuits are given to measure small capacitance changes. The capacitance, or simply capacity, of an isolated conducting body is defined as Q equals C times V. Here Q is the charge on the conductor and V is the potential, relative to infinity, where the potential is zero by definition. To put it differently, when a charge Q from infinite distance is transferred to conductor, its potential becomes V proportional to Q over C. In practice, we have a set of conductors instead of just one conductor. When a charge Q is transferred from one conductor to another, the result is a voltage difference. Voltage V difference equals simply our Q over C. So the conductors are oppositely charged with Q and minus Q is respectively, so that we can see plus Q and minus Q. Again, for this pair of conductors, Q proportional C times V, where V is the voltage difference between these conductors, right? Usually, the capacitance is defined between two conductors. This capacitance is determined exclusively by the geometry of the complete set of conductors and the dielectric properties of the non-conducting matter in between the conductors and not by potential of the conductor. The set of conductors is called a capacitor. A well-known configuration is a set of two parallel plates. The flat plate capacitor with capacitance according to this equation on the right side. The parameter epsilon here is called the permittivity and describes the dielectric properties of the matter between the conductors. It is written as the product of epsilon, not the permittivity of free space or vacuum. Its value approximately 8.8 times 10 in power minus 12 farad over meter. And epsilon are the relative permittivity. The latter is also called the dielectric constant of the medium between the conductors. For vacuum R as equal 1, for air and other gases, the dielectric constant is fractionally higher. Liquid and solid have larger values, as you can see from this table. For all kinds of configurations, the capacitance can be calculated. Two straight parallel conductors, as you can see on figure A, as here in this part, with radius A and a center or spacing G, have a capacitance per unit length according to this equation. A coaxial cable, when we have two concentric cylinders in figure B, as you can see in figure B, with outer diameter of center conductor and the inner diameter of the shield B has a capacitance per unit length equal on the right side of this formula. The capacitance of other, less symmetrical configuration can be calculated analytically. For instance, consider a plate-plate capacitance, as we can see on the right figure C, with rectangular top electrode with W2 and length L, opposed to the long strip electrode with a distance L. The capacitance of this structure, as often encountered in capacitive displacement sensors, is expressed as follow equation on the top. This is a big non-usual equation. Anyhow, for a homogeneous dielectric, the capacitance can always be written in the form as a more simple, as you can see here, where the G is a geometric factor. For the parallel plate capacitor with plate distance G and infinite plate dimensions, G may be expressed as A over G. When the plates have finite dimensions, as for instance for the structure, G can still be approximated by simply A over G. We discussed the conditions for these approximations a bit later. Most capacitive sensors for mechatronic applications are based on changes in the geometric factor G, thereby assuming a constant value of epsilon. As far as a fair approximation, the value for the dielectric constant epsilon of R can be set of 1. At small changes of A or D, however, deviation from this value must be taken into account because the capacitance C changes, as we can see for the next expression here, where we have some expression in differentiation in differential equation. As the next expression, we might find the expression of the PD, PC, and PW are the partial vapor pressure of respectively dry air, CO2, and water vapor in millibar. So at coefficients AD, AC, AW, and BW are empirical parameters, and T here in all of this expression is absolute temperature. Furthermore, due to relaxation effect, epsilon appears to be frequency dependent. The dielectric constant is expressed in complex notation. So we may express as epsilon equals epsilon stretch minus J epsilon double stretch, where both the real and imaginary parts are frequency dependent. For water, the frequency dependency is expressed as this expression you can see in this equation. Analytically, we can find minus 2.3 times 10 in power minus 6 for the in temperature. Temperature exact can be minimized using balancing technique and proper electrode material. Humidity cannot be ignored in high precision capacitive displacement sensors. Either the temperature should be kept sufficiently for about the dew point temperature or humidity effect and must be avoided through the use of special design. Many capacitive displacement sensors are based on flat plate capacitors, as you can see on figure A. Either the plate of distance D or effective plate area A, as you can see in the middle, is used as a position-dependent parameter. Other shapes are also used as displacement sensors. For instance, the cylindrical one on figure C, on the right side of this slide. When using the approximated expression, an error is made due to the stray field or fringes at the edges of the plate. The practical implication of this error is a nonlinear relationship between displacement and capacitance. The effect of stray fields can be reduced by the application of warping. One electrode is grounded, the other active electrode of the capacitor is completely surrounded by additional conducting electrodes in the same plane and isolated from the active electrode, as you can see on figure A. The potential of the guard electrode is made equal of that of the active electrode or active guarding using a buffer amplifier. The result is that the electric field is homogeneous over the total area of the active electrode, assuming infinite guard electrodes and the zero gap between the two electrodes. However, since the guard electrode has finite dimensions and the gap width isn't zero, so residual error occurs here. This error depends on the dimensions of the guard electrode and the gap width. It's usually at the two inequalities here. With D is the plate distance and X is the width of the guard electrode. You may see on these pictures on both sides. As a rule, so as this electrode, and here we have another expression as S. S is the gap width between guard and active electrode. As a rule of thumb, for X over D and D over S equal to 5, this errors less than 1 picometer. Finally, when the plates are not exactly in parallel, that's very difficult to get exactly, right? So the relative error in this case at a skew angle alpha is of the order alpha 2 over 3. For 1 degree or near 0.017 radian, this corresponds to an error about 10% on. Capacitor sensors are very useful for the measurement of displacement, utilizing variation in the geometric factor G. If one of the plates is part of deformable membrane, pressure can also be measured by using the capacitive principle. Generally, electric fields are better manageable than magnetic fields because by active guarding, it is easy to create electric fields that are homogeneous over a wide area. And this is the major reason that displacement sensors based on capacitive principle have excellent linearity. This slide shows schematically two basic configurations for linear displacement. The moving object of which the displacement has to be measured is connected to the upper plane. In this example, the parameter A, effective surface area, varies with displacement. In left figure 8, a linear displacement of the upper plate is indicated. Direction introduces a capacitance change, which is. So in ideal situation, delta C is proportional to epsilon delta X times A over D, or relative changes in the middle formula, delta C over C, proportional delta C X over X. All other parameters need to be constant during movement of the plate, right? Okay. Capacitive sensor for rotation can be configured in a similar way, with segmented plates rotating relatively to each other, where the distance d remains a constant. So, to assume a linear relation between the displacement and the capacitive change, Active guarding has to be applied in all cases. In figure B, on the right side of the picture, you can see this, and this figure shows a differential transducer. We have a displacement of the upper plate caused by two capacitors to change simultaneously, but with opposite sign. So we have delta C1 proportionals minus delta C2, or its proportionals as we can see in the first expression, epsilon delta X times A over D, right? Okay. The initial position is defined as the position for which C1 should be equal C2. For this position, we have delta Ex equals 0. And the change in A or D due to, for instance, plate, backlash, or temperature change. Does not introduce a zero error, as long as both capacitance changes are equal. An additional advantage of the differential configuration is the expanded dynamic range. What it means? It means in the reference or initial position, the capacitance of the two capacitors are equal. Yes, right. So since only the difference in process, the initial output signal is 0. And a small displacement results in a small output signal that can be electronically amplified without overload problems. A single capacitance in the initial position may produce a considerable output signal which cannot be amplified much more, unless it is first compensated by an equal but opposite offset signal. However, compensation by an equally shaped sensor is more stable than compensation in the electrical domain. A disadvantage of the configuration with is shown in previous figure is the electrical connection to the moving plate required for the supply and transmission of the measurement signal. And this figure shows the configuration without the need for such connection. The moving plate acts here as a coupling electrode between two equal flat electrodes and a readout electrode in the middle. All fixed electrodes are in the same plane. In the initial position, the coupling electrode is just midway the two active plates, supplying by sinusoidal signals with opposite phase. In this position, both we have balanced position signals are coupled to the readout electrode, where they cancel, resulting in a zero output signal. When the top electron shifts to an off-center position, the coupling becomes asymmetrical and resulting in an output signal. This signal proportional to the displacement and with a phase indicating the direction of the movement. Using the simplified model on figure B on the bottom part of the slide, it is easy to verify that the current through the readout electrode satisfies. So we should notice that C3 does not change with displacement because its surface area remains unaltered. In case when we have V1 equals minus V2 and it's simply as Vi, the output current I is directly proportional to the capacitor difference. Capacitance difference is C1 minus C2. C1 and C2, as you can see. In a differential configuration, C1 equal be C naught plus delta C, and C2 is C naught minus delta C. Okay, so the output current appears to be proportional simply to delta C and consequently to the displacement delta X, right? As you can see from the figure A. Do you agree with me? Okay. So its phase in either plus pi over 2 or minus pi over 2, according to the direction of the displacement. It should be pointed out that proportionality only holds when fringe field effects are small, or when these fields are eliminated by gradient. An alternative readout scheme is shown in a previous figure, and two adjacent plates are supplied with two sinusoidal voltages with phase difference pi over 2. In this case, the voltages are capacitively coupled to the common readout electrode via the moving plate of the capacitor, and similar to the design in a figure A on the left side of this slide. When the moving electrode is just opposite the left plate, the phase of the output current is just pi over 2, according to the first equation in this slide. Okay? When the electrode arrives just above the right plate, the phase is pi. And when moving from electrode, one electrode to the next, the output phase changes gradually over p over pi over 2 radians. So, to calculate the phase of the output current, independent of the displacement, we define the coordinates according to the figure B, so that we have 0, minus pi over 2, pi, plus pi over 2, and 5. Okay? The center of the moving plate runs from the x equals 0 to x equals pi, p, sorry. For simplicity, all plates have equal widths p. And suppose now the input voltages are like this first equation, very simple, V1, V times sine omega t, and V2, V times cosine omega t. The output current equals to for another expression as this. The capacitance C1 and C2 have the value of value epsilon AW over D is proportional C stretch over W, with a constant plate length and W the effective width running from P to 0 for C1 and from 0 to P for the C2. Okay, this so substitution in previous equation will result in next equation for this part, and we can this as a very simple expression, what I times the cosine omega t plus p. And only in this case on the left side we can find the coefficient k is a constant. So the phase angle satisfies the relations here we may got from this simple expression. The phase varies with displacement in a slightly nonlinear way. We can see here in this diagram, generally linear in the middle part, but on the initial and the final parts in a nonlinear. Great fields cause further deviations from linearity, but even with guarding, the relation is essentially nonlinear. This is we can see from the corner effect in both sides. However, by modifying the electrode shape, it is possible to get an almost linear relationship. Capacitive displacement sensor can also be configured in a cylindrical configuration, as you can see on figure C. The principle is the same in a cylindrical setup, but in cylindrical setup is a more compact and has fewer straight capacitances and therefore a better linearity. This type of capacitive sensor is called a linear variable differential capacitor. The sensor exhibits extremely good linearity. What it means? It means better than all dot 0.01% and allow temperature sensitivity down to 10 picometers per Kelvin. The rotational version of the linear variable differential sensors, linear variable differential capacitors, is the sensor exhibits extremely good linearity, as I mentioned, better than 0.1%. And another rotation variable differential capacity we may compare is characteristic. It is based on the same principle, but configured for angular displacement. So angular sensitivity is obtained using triangularly shaped electrode. And further specifications on this sensor are given in the overview table. The lower limits of linearity, stability, and accuracy of these precision sensors are set by the air humidity. What it means? It means the water vapor in the air might condensate in edges and small gaps of the construction, like capillary condensation. And in this case, we have locally replacing air with dielectric constant about 1 by liquid water with epsilon r nearly the 80 according to this table. Okay. Even at temperature above the dew point, water vapor might condensate due to contamination. It's maybe hygroscopic particles that attract water molecules and act as a condensation nucleus. This means that for the highest performance of temperature of the sensor should be kept well above the dew point of temperature. The measurement range of the linear capacitive sensors discussed so far and is limited to approximately with the beats of the moving plate. Look at this side, please, so that we discussed it. Kyle already is doing. And we have a graphical amplifier, how this is working here on this place. Okay. However, the range can simply be extended by repeating the basic structure of the previously discussed configuration. In upper figure A, this shows this concept. It consists of an array of sections similar to the one in previous figure. When the moving plate approaches the end of one section, it is simultaneously enters the next section. The fixed electrodes in the array are connected to sine wave voltages with phase differences of pi/2. You know, remember, only sinusoid and cosine have the same phase difference. When the moving plate travels along 4 successive sections, the phase of the voltage of this plate changes from 0 to 2 pi, as you can see from figure B. So we can see over 2 pi, 4 pi over to 2 pi to the from 0 to pi. From pi to 2 pi, we have this one. Okay. So this is repeated for each group of 4 electrons. Hence, the output phase changes periodically with displacement, with a period of 4 times the plate pitch of P. And we can see from 0 to 4P, we have from 4P to 8P and 12. And ambiguous output is obtained by keeping track of the number of past cycles using an incremental counter. The straight lines in figure B, as you can see here, this straight line are actually 4 S-shaped curves in series. But non-linearity can be compensated for the appropriate shaping of the fixed electrode. Phase differences can be measured with high resolution, down to 0.1 degree. By periodically repeating the structure, a large range is obtained combined with the high resolution. A well-known application is found in some electronic caliper rules. These have a range of about 20 centimeters and a resolution of 0.01 millimeter. Capacitive angular sensors operate in a similar way. You can see these in this slide. The fixed segment plates are arranged in a circular array, and the moving plate is a vane connected to the rotating shaft, so that you may see in two positions. The challenge of the designer is to obtain the highest possible resolution over the fixed range of 2 pi radians. Various solutions have been proposed. For instance, multiple electrodes on the moving part. But evidently, guard electrodes are indispensable here to reduce straight field. The resolution of capacitive multiplate angular sensors can be as high as 18 bits or 5 seconds of arc. Silicon micromachining technology offers the possibility to construct extremely small capacitive sensors. As you can see in this figure, as less than your fingertips. The technology allows the fabrication of very thin membrane, similar to piezoresistive sensors, as described earlier, resistive sensors. Instead of adding piezoresistor to the shaping element, the flexible membrane is opposed to the fixed flat electrode, building a miniaturized flat plate capacitor. An applied force of pressure difference causes the membrane to deflect, as a resulting in a capacitance change that can easily be measured. Advances in the technology of MEMS, micro machine capacitive sensors, have resulted in the realization of microsensors for the other quantities as well. For instance, acceleration. These systems now find widespread application in automotive and other large volume market segments. This technology are highly attractive for accelerometers, rate gyroscope, and gas pressure sensors, but less for force sensors because of the susceptibility of mechanical damage of the tiny movable parts. Accelerometers get much attention because the force is introduced simply by the inertia of a seismic mass, fabricated on the same chip. Capacitive sensors for other measurements are also considered to be implemented in MEMS technology. For example, the angular sensor. From a technological point of view, however, a capacitive sensor is more difficult to realize compared to its resistive counterpart. The surfaces of the various parts making up a capacitance and should be provided with a conducting layer acting as one of the capacitor's plate plates. Moreover, the spacing between the plates should be made small to obtain a reasonable capacitance and sensitivity. And the alignment of the two electrodes is also a critical processing step. The first silicon capacitive pressure sensor consists of a stack of 3 layers. And you can see on this left figure on the A, you can see as the 3 layers. We have here as a support layer, membrane or edge silicon, and the top layer with a fixed counter electrode. The support layer and top layer can be made from silicon or glass. The electronic circuitry resides on the membrane chip or the silicon top layer. The layers are connected using special techniques. And namely, this figure shows some examples of integrated capacitive pressure sensors in vertical scale much larger than horizontal scale. In the next configuration B, The electronics and the membrane are made from separate wafers to enhance technological freedom. The processes for etching membranes and deposition of electronic circuitry are not fully compatible. The figures show only a general layout, and details can be found in more research papers. A large variety of alternative structures have been proposed over the last decennia. So often, the membrane chip is positioned flipped at the top, whereas a reference capacitance is included in the structure. A structure without separate top layer. And both capacitor plates are constructed on the membrane chip using surface micromachining. The gap is realized by selective etching of a so-called sacrificial layer positioned between the two electrode layers. So here too a reference capacitor intensive to pressure and has been integrated. And due to the small dimensions of the structure in order of millimeters, the capacitance value is small too, and the change caused by the measurement is even smaller. Initially larger capacitance may be realized by reducing the gap distance between the plates. However, electrostatic or attractive forces between the plates can be easily resolved in buckling and short circuiting of the capacitor. The alternative is to increase the effective surface area, and this can be realized by supporting dielectric structure. The sensor is made up of two process buffers put together face to face and resulting in a narrow gap between them. After bonding of the two wafers, the substrate of the top layers is removed by selective etching, leaving a thin membrane near the 2.5 micrometer. As a reminder from the top wafer, the membrane is supported by hexagonal grid of a dielectric material that prevents it from collapse. In this way, a relatively large area combined with a narrow cap is achieved, and hence a large capacitance and sensitivity can be obtained, and same with other techniques. Many accelerometers are based on capacitive sensing techniques. For instance, the accelerometer with feedback as uncertainty aspect. A few decennia ago, it was shown that the complete system can be integrated on silicon and resulting in a small, easy-to-mount device. Capacitive accelerometers made in MEMS technology are basically structured as given in this slide. We have here a piezo or resistive accelerometer, and they consist of a seismic mass suspended on flexible beams. Instead of integrated piezoresistors, electrodes are deposited on proper places in the structure, forming flat plate capacitors. The mass moves due to an inertial force, resulting in a change in distance between the plates. And this causes the capacitance to change. By a special configuration with 3 or even 4 masses and associated electrodes, it is possible to realize a 3D accelerometer in a single piece of silicon. Together with the MEMS sensor, additional electronics and signal processing, for instance, voltage regulators or ASIC application-specific integration circuit, and temperature sensor for offset compensation, all of that can be housed in a small package. Micro-machined acceleration sensor suffer from small capacitance too, and hence have low sensitivity. A large initial capacitance might be realized by dielectric support structure. See the preceding section on a pressure sensor. Another way is to increase the effective surface area. This is realized in MEMS technology, allowing the construction of so-called comb structure. and namely this slide shows the basic configuration. When the two combs move relative to each other in the direction of the arrow, the effective surface area of the capacitor changes. The more fingers, the larger the surface area, and the higher the capacitor. Such structures and even more complicated configurations can be gradually made using advanced MEMS technology. The same structure is also used for capacitive actuators, so-called comb drivers. Comb drivers in this case. So, and now we will be studying another part of interface. In a high-resolution sensor and micro sensor, the capacitance changes that have to be measured and can be extremely small, down to fractions of a femtofarad, or nearly 10 in power minus 15 farad, femtofarad. Adequate interfacing is required to preserve the intrinsic performance of the sensor system. We discuss four major analog interface methods for capacitive sensor, according to this figure. It may be four. First is impedance measurement, preferably in a bridge. Second, current voltage measurement with operational amplifier. Third, frequency measurement. And fourth, time measurement, charging the discharging capacity with constant current. For each of these methods, we give a brief analysis. The bridge transfer on the first figure, and you may see according to this equation. In a single sensor configuration, when C equals the C plus delta C and C2 equals C, hence you may get the second equation for V naught over VI. It's negative sign before it. The transfer is frequency dependent, but non-linear. In a differential or balanced configuration, C equals C plus delta C, and C2 is a C minus delta C. And thus we can get third equation, as you can see, simple here, very simple expression. Okay, so clearly the differential mode yields better linearity and a wider dynamic range. A proper measurement of the bridge output voltage requires a differential amplifier with high input impedance and high common mode rejection ratio. Interface circuits based on current voltage measurements are shown in figure B and C. Here, this one. And here you may see interesting. The first used in figure B used for single mode operation, and the C is used for the differential mode operation. If resistance R is disregarded, the transfer function of the single mode circuit looks like this first equation. V naught over V over I proportional in C plus delta C over CF. Again, the advantage over balanced configuration appears immediately from the last expression on this of the right side, which is linear, and the output is zero in the initial state when we have equal capacitance. The transfer is frequency independent if resistance R in figure C is left out. However, the circuit does not work properly in that case due to integration of the offset and bias current of the operational amplifier. The resistance R prevents the circuit from running into overload, but causes the transfer to fall off with decreasing frequency from about F proportional as this expression, 1 over 2 pi RCCF. And this means that the frequency of the interrogating signal V should be chosen well above these cutoff frequencies. The sensitivity is limited by the stability of the initial state. Initial state where the output should be zero. Neither the amplitude, drift, and nor the frequency instability of the oscillator affect the zero stability, since they are common to both differential sensors. The performance of the measurement is mainly limited by the phase difference between the two AC voltage sources. The output appears to be very sensitive for deviation from the required 180 degrees phase difference, a fact that can be used to create a sensitive capacitance to phase converter. A simple, though rather inaccurate method for measuring capacitance changes in the conversion to frequency, and shown on figure D, here on the bottom part, left side. The capacitance is part of LC oscillator circuit that generate a periodic signals with frequency, and we may see from this equation. And another part, when we have in this case in our D, as a frequency in this case, F proportionals 1 over 2 pi times square root from LCI. For simplicity, they can be expressed according to this expression. F here is the frequency in initial state. An advantage of the oscillator method is easy signal processing with a microprocessor. What it means? It means the frequency can be determined by simply counting the number of clock pulses during one cycle of the oscillator signal. Obviously, the other circuit elements must be stable, and the oscillation process should be guaranteed over the entire capacitance range. The interface contains a microprocessor control feedback system with a voltage control oscillator, which keeps the actuation frequency equal to the resonance frequency of the LC sequence, so that we have proportional LC. And this interface has a sensitivity of 100 Hz over F and a resolution about 0.1. An interface sequence that combines the advantages of a time signal output and high linearity is given on the last figure here. An example of a relaxation oscillator. The unknown capacitance is periodically charged and discharged with currents I1 and I2. During charging, we see, as we can see we see increases linearly with time until the upper hysteresis level of the Schmidt trigger is reached. At the moment the switches turn over and the capacitance is discharged until the lower hysteresis level is reached. The result is a periodic triangular output signal with fixed amplitude between the levels of the Schmidt trigger and a frequency related to the capacitance according to this last equation, where Vs here is the hysteresis range of Schmidt trigger. The method yields accurate results because the frequency depends only on these fixed levels and current charge current. In the previous section, the sensing device is always a capacitor, of which a particular parameter, A, D, or epsilon, changes due to a measurement. The alternative of this so-called internal capacitance is the external capacitance that changes by human presence. In embedded system, of a common way to measure capacitance is by measuring the time of charge or discharge this capacitor or capacitive sensor. The use of an RC network allows the designer to set the order of magnitude of the measured charge change time And this enables also a trade-off in the implementation between sample time and resolution. How it been realized? A long measurement time allows for a high resolution or many time steps, but also allows sample rate caused by the time between measurements. The method is suitable for both external and internal capacitors. And this figure shows a schematic method for measuring externally caused variations in capacitance using a microcontroller. One side of capacitor is formed by a piece of conducting material, such as an antenna or section of foil. One pin of the microcontroller is used to charge this capacitor. The other pin is used as digital input to detect the moment when this charge voltage exceeds a certain level, normally defined by the logic level of the digital input. In a 5-volt microcontroller system, such as the earlier discussed Arduino, this level lies around 2.5 volts. And this means that the capacitive sensor is charged until it reaches, namely that value, 2.5 volts. After this, the capacitive sensor can be fully discharged by making the detection in and output, simply by short-circuiting the capacitor to completely discharging it. As soon as the capacitive sensor is completely discharged, the cycle can be started again. But we should be noting here that no analog voltage is measured, and just the time it takes to fully charge the capacitor formed by the foil and human presence. A similar approach can be used for measuring an internal capacitor, as we can see in this slide. The resistance value R has to be chosen in a range such that the charge time and can be measured with sufficient resolution by the microcontroller system. The described method uses the microcontroller input and output pins to charge, discharge, and detect the voltage level of a capacitor. Instead of sensing a change in capacitance, the voltage used to charge the capacitor and can be measured using this strategy. With fixed values for the capacitor and resistor, so a fixed value over C, the charge voltage, and will be determined by the input voltage. This approach allows for a simple, albeit nonlinear, analog to digital conversion, which can be implemented using a single microcontroller pin. Since the nonlinearity is highly predictable, it is a first-order RC network, the relation between measured time and input voltage can be linearized. And this figure shows an Arduino board with breadboard and RC network near 100 nanofarad and 100 kilowatt, and a potentiometer as analog sensor of voltage source. In this case, the voltage is measured simultaneously with one of the analog to digital converter input pins and with the RC network connected to pin 2. By making pin 2 as an output, the capacitor can be fully charged or fully discharged. After switching back to input, when we have high impedance, the capacitor will be discharged or charged. Well, sinusoidal, so it's no matter from which position will be started. By the sensor voltage supplied by the potentiometer, acting as a position sensor here. The charge time T depends on V from T, and V from T we may express it as a V source times 1 minus E in power minus T over RC. Here we have fixed value R and C. And this strategy allows turning any regular microcontroller pin into an analog sensing pin, especially when the amount of analog input is limited or unavailable. This approach might be beneficial. Commercially available optical array sensors, like the one shown in this figure, already have built-in capacitors for this very purpose, taking into account the usually limited availability of analog input on conventional microcontroller systems. Although the sensor is in the optical domain, the applied interfacing strategy is capacitive. Capacitive sensors are suitable for the measurement of all sort of position-related quantities, like displacement, rotation, speed, acceleration, and tilt, combined with an elastic element like force, pressure, torque, and mass sensor can also be realized using capacitive principles. So all of this. Most of these sensors are based on the previous equation and indicating the relation between the capacitance value and geometric parameters, like effective surface area and plate displacement. Capacitive sensors are particularly suitable for applications with high demand, for instance, extreme temperature. The mechanical construction is simple and robust. Moreover, extremely small capacitance changes down to 1 farad can be measured with simple interface signals. And finally, stray capacitance and other capacitance due to the wiring and simplifier can easily be eliminated using guarding, virtual guarding, and proper interfaces. As with all displacement sensors, capacitive displacement sensors can be modified to make them suitable for the measurement of angular rate, acceleration, force, torque, mass, and pressure. Differential configurations are recommended and, where appropriate, a feedback principle as well to reduce intrinsic sensor error. In case when we refer to uncertainty aspect for a capacitive accelerometer based on feedback. And namely, this table resumes some specifications of commercial capacitive sensor for various measurement quantities. Using the circular multiplate capacitor, angular position and angular speed can be determined with high accuracy, as has been demonstrated in many papers, research papers, first of all. With a careful design, angular position sensor can have a resolution of 18 bit and reproducibility of 17 bit and an absolute accuracy better, less 14 bit. A micro machining contract-free angle sensor, this angle sensor combines an inductive principle for the transduction from angle with respect to a fixed magnetic field, to the deflection of a polysilicon micromass, and the capacitive measurement of this deflection. A planar micro machine gyroscope with a balanced capacitive readout circuit. A graphical impression of this micro machine structure, as can be found in gyroscope and accelerometers, is shown in this figure, and you can see this representation. With capacitive sensor, the torque on rotating axis can be measured. In some of these applications, the sensor on this axis is purely passive, which means that no power supply on the axis is needed. The information transfer to end from the axis is accomplished other activity, inductivity, or with pure capacitive techniques. The capacitive mass sensor uses a metal spring as an elastic element. This sensor is designed for a low temperature sensitivity, for which thermally stable materials have been selected. The capacitive force sensor contains an elastic dielectric. Its basic configuration is depicted in this figure. It is sensitive to the two shear directions and the normal direction. At 0 4, all four capacitance C1 and up to C4, as you can see on this right corner, all four capacitance are equal. A pure normal force will increase each capacitance equal, and a pure shear force results in an increased difference between adjacent capacitance, or differential mesude, according to the direction of applied shear force. The interface should be able to distinguish between these force components. In this section, examples of capacitive measurements for a variety of applications are discussed, illustrating the versatility of the capacitive sensing mesude. Selected measurements are distance, displacement, thickness, rotation, strain, force, level, and flow. Some special applications concern the detection of persons and rain on a car's windscreen. Capacitive sensors offer the possibility of highly accurate distance or displacement measurement, having control XY table. A capacitive sensor designed for product inspection. The goal is to measure the inner diameter of cylinders using a coordinate measuring machine with touch probe. In this work, the bending of the touch probe or a thin stylus is determined by capacitive means. The mesude allows measuring of internal diameter less than 0.3 millimeters with accuracy of 1 micrometer. Coating thickness can be measured in several ways. For a non-conductive coating on a conductive plate, the capacitive mesude is suitable to measure the thickness of such a coating. An example of this mesude proposing a capacitive probe and giving an analysis of the various source of error. Multiple plate capacitive sensors were discussed to enlarge the range of a displacement sensor. An alternative solution where a configuration is presented similar to the induction on inductive sensor. The sensor consists of two printed circuit boards, and each provided with an array of electrodes or transmitter and receiver, and able to slide linearly over each other as an optical encoder. The signal transfer from the transmitter to receive is determined by the configuration of the electrodes and shows a triangular course with displacement. Also realized with simple technology like PCB, copper electrons, and coating, and the resolution of the sensor appears to be about 126 nanometers over a range of 20 millimeters. Not only a linear displacement, but also rotation can be measured accurately by capacitive means. The classical example is a trimmer or rotary capacitor, which uses a series of parallel plates with overlapping regions. Rotating one set of the plates will change the total activity surface area of the capacitor, as you can see from this figure. An example with segmented electrodes was given in this slide, a modified version having a completely isolated rotor. The main advantage of this design is that no electrical connections to the rotating part are needed, and the challenge of the designer is to obtain the highest possible resolution over a fixed range of 2 pi radii. Various solutions have been proposed. For instance, multiple electrodes on the moving part. Evidently, guard electrodes are indispensable here to reduce stray field. The resolution of capacitive multiplied angular sensor can be as high as 18 bits for 5 seconds of an hour. A totally different application of a capacitive sensor is the measurement of tire strain. Car tires are usually reinforced with layers of steel wire. When the tire is loaded, the resulting strain causes the distance between these wires to increase, and hence the capacitance between the wires change accordingly. The interface is based on an oscillator, like we see on figure D, this one. But instead of the LC oscillator, an RC oscillator is chosen. Wireless readout allows strain measurement during rotation of the wheel with tire. Another approach to measure tire strain using a capacitive machine has been fabricated a particular strain gauge consisting of a pair of interdigitated flat electrodes on a flexible polyamide carrier. The gauge glued onto the inside tire responds to strain by a change in capacitance. Next lecture will be inductive and magnetic sensor. I hope this is enough for this moment, and I hope you enjoyed this lecture, and I'm looking forward to see you next time. I want to remember, if you have any questions or propositions, you may ask me directly under the video. Good luck. See you later.